Hi everyone, we are finally to the point in chapter 5 where we are using different lapse rates to find the base of the cloud, where the cloud starts its rise. Very important for pilots so that they know if they can go on visual flight rules or instrument flight rules. And we are also going to compare different lapse rates to look at cloud temperature, which helps us to predict what type of precipitation we'll be having from this cloud. So let's get started. Brief review. When we looked at one type of lapse rate, the environmental lapse rate, we use that to describe the stability of the atmosphere. And so we talked about stable atmospheres, unstable atmospheres in terms of the environmental lapse rate. And in terms of that, now we're going to look at the cloud base, or the starting altitude of the cloud, and the cloud temperature within the cloud by comparing two different lapse rates, a parcel lapse rate and a dew point lapse rate. And by doing that, we are going to look into the vertical start of the cloud and the vertical temperature of the cloud by comparing these two different lapse rates. And in terms of that, that becomes really important because you can see that in a stable atmosphere, you can have different altitudes for the start of a cloud. This fog starts at ground level in a stable atmosphere. This cloud in a stable atmosphere starts at 1,000 meters high, maybe 1,500 meters high in the Grand Canyon. So you can have different altitudes for that cloud base. We can calculate that. In an unstable atmosphere, you can also have different altitudes for a cloud base. This huge cloud in the unstable atmosphere is closer to the ocean surface. This cloud starts above a mountain surface. So cloud base information is critical for predicting weather, and it's critical for pilots. When we are comparing these two lapse rates, we are comparing what is called adiabatic lapse rates. And adiabatic is a word that literally means prevented from interacting. And in describing these adiabatic lapse rates, they are imaginary parcels that are prevented from interacting with the environment around them. In other words, these parcels are like balloons that are separated from the environment around them. And we are comparing two different balloons with adiabatic rates. When we were looking at the environmental lapse rate, that is reflecting everything that is going on in the environment. The changes in pressure, the changes in temperature, the changes in water vapor molecules, the changes in ozone molecules, many different types of issues come into play when we look at the environmental lapse rate. When we put a parcel into a balloon, the only thing that we are going to be looking at is the pressure of the environment on the surfaces of the balloon. We are not going to be exchanging energy or heat with the environment because we have this surface, imaginary surface, between us and the environment. We are not going to be exchanging molecules of water vapor or molecules of ozone with the environment because we have this surface that has sealed in air that started at the surface. And we are only going to be able to look at expansional cooling temperatures inside the parcels. We are going to be looking at a surface air parcel that is called a dry adiabatic lapse rate parcel, or a dry parcel. And we are going to be looking at a dew point parcel, which is a parcel taken from the surface and at the dew point temperature. So the important thing to take out of adiabatic lapse rates is that the only interaction that they have with the environment around them is the pressure that is pushing against their surface. At higher altitudes, you have less pressure pushing against the surface, so the molecules within this balloon can expand and cool and change the temperature of the balloon. Let's look into that a little bit more. When we talk about a dew point adiabatic lapse rate, we are talking about a parcel of air that we gathered right at the surface, and we gathered that at the dew point. It is a parcel of imaginary air that has 100% water vapor in it. It is total water vapor at the dew point that we collect in an imaginary parcel at the surface. And the dry adiabatic lapse rate parcel, or the dry parcel, is an imaginary parcel of air that we collect at the surface that does not have 100% water vapor. This is regular air. It has between 1 and 4% water vapor. It is unsaturated air because it is not condensed. It's not a layer of fog that we are picking up at the ground surface. Remember, fog actually moves up a few inches from the ground surface at the very lowest. So we are picking up this unsaturated air right at the ground surface in an imaginary parcel, and we are sending it up into the atmosphere to expand and cool. And we are sending our dew point parcel up into the atmosphere to expand and cool. In doing so, we can start to find out where this dry parcel will meet the temperature of the dew point parcel and start condensing into a cloud. Let's look into that a little bit more specifically. When we send a dry parcel of air up from the surface, it is going to rise and cool and expand faster than a parcel of air that might have more moisture in it. And you know that makes sense because in your specific heat experiments, you compared the ability of dry soil to absorb heat versus water to absorb heat, and you found that the dry soil absorbed heat faster. And you found that the dry soil emitted heat faster and lost that heat faster than water. And so it makes sense that that water has an effect, and that dry gas can cool faster than a gas that has more moisture in it. We say that the dry parcel is unsaturated because it's not condensed. We say that it loses warmth easily, like the dry soil lost warmth easily. We give it a calculated rate for losing that temperature, and that calculated rate for the dry parcel is at 10 degrees Celsius per 1,000 meters. For every 1,000 meters the parcel rises, it will lose 10 degrees Celsius. The 30 degrees Celsius parcel at ground level will rise and expand and cool so that at 2,000 meters it is now 20 degrees Celsius lower in temperature. That's a really substantial drop in temperature over altitude. We noticed that kind of a drop when we were looking at environmental lapse rates and unstable atmospheres. We are using this imaginary lapse rate for the imaginary parcel that is the dry parcel. If we look at it another way, we have a lapse rate that is pretty low down. The conditionally stable lapse rate of 6.5 degrees Celsius per 1,000 meters had a more moderate slope to it. This has a more dramatically lower slope to it. It is losing more temperature per 1,000 meters. When I think about the dry adiabatic lapse rate, I give myself a mnemonic that it is the lots of loss of heat kind of lapse rate. You might think of it in another way. I hope that helps you out a bit. When we talk about the dew point adiabatic lapse rate, we are talking about a parcel that we collected at the surface in an imaginary parcel that is at the dew point temperature and is at 100% water vapor. There is no oxygen in this parcel. There is no nitrogen. There's no argon in this parcel. It is 100% water vapor in this imaginary parcel. We say that the parcel is saturated because it is 100% water vapor, and therefore it will lose warmth slowly. We know that from our specific heat experiments. We give it a calculated rate of losing warmth at 2 degrees Celsius per 1,000 meters. That 2 degrees Celsius per 1,000 meters sounds familiar. It sounds like a really stand-up straight lapse rate that we talked about with environmental lapse rates. And it is a much different lapse rate from the 10 degrees Celsius per 1,000 meters. So that if you start off with your water vapor parcel at the dew point of, let's say, 14 degrees Celsius, your dry parcel is starting off at 30 degrees Celsius because it is regular air at the surface. But this is air at the dew point. It starts off at 14 degrees Celsius. And we know that when the regular air meets the dew point, you will have a cloud. When we can get that intersection of the dew point adiabatic lapse rate and the dry adiabatic lapse rate, we will have the cloud base. So let's take a look at it. We started here at 14 degrees Celsius at the dew point. Go up 1,000 meters, minus 2 degrees Celsius, 12 degrees Celsius. Go up 2,000 meters, another 2 degrees Celsius off, we get to 10 degrees Celsius. On the other hand, you saw that the dry adiabatic lapse rate started at 30, lost 10 degrees Celsius to 20, lost 10 degrees Celsius to 10. At this 2,000 meter level, the parcel that has the dew point temperature is equal to the parcel that has the air temperature from the dry parcel. They meet. That is a good base altitude for a cloud to condense and start climbing from there. You can remember the dew point adiabatic lapse rate of 2 degrees Celsius by 1,000 meters. But just remember, like, dew point is like duo, when a duo is 2. So I hope that helps you out. In terms of looking at the adiabatic lapse rate, we look at the intersection of the steep dew point adiabatic lapse rate and the really gentle dry adiabatic lapse rate, the really low lapse rate for the dry parcel. Where they intersect is known as the LCL, the lifted condensation level, the cloud base, the base of the cloud here. It is usually reported, it can be reported as an altitude, but it is often reported as a pressure measurement. You saw on the soundings that the altitudes that were here were often matched pressures. So you'll see a LCL at 950 millibars, pretty close to sea level. Or you might see it up at 600 millibars, quite high in a desert environment. When you want to look for an LCL, the first step is to plot the surface temperature for your parcel and to start noting the dry adiabatic lapse rate per 1,000 meters. Then you plot the dew point parcel at the dew point temperature from the surface and add in that dew point adiabatic lapse rate of 2 degrees Celsius per 1,000 meters. When you find the triangulation point, that is the lifted condensation level. That is after the forced lift by topographical means or